Okay, let's start session 3. Now we're going into the main topics in our math chem. The first we'll be talking about real numbers. Okay, so basically, even though I said real number, what we're starting is just getting a recap for our calculus analysis course. So in summary, we'll be starting our review of calculus, or in analysis to be exact, because we'll be talking more about basic analysis course. Will be more about basic analysis courses, so kind of different from the basic calculus courses that you have taken in undergraduate, so just keep in mind. So before we start, we'll start with motivation again, which is, so what is basically our objective for learning calculus and analysis? It's not that hard, but then when you think about it, when you're studying economics, don't feel like you're really using the calculus or analysis subjects that you learn in the classes in mathematics department. So you might be wondering, where are we using this if you learn this in economics? So let me just get a recap and just take you some tour onto how it's related to economics. Don't be alarmed by this long text. We're not gonna fully understand it. I'm just kind of showing this to show how we're using calculus analysis in economic settings. So I just wrote some question on the slides. It's basically how economic question, but while solving the question, we have to use some properties in analysis and calculus. So let me just talk about it there very briefly. So a lot of the economic questions, especially if you take micro theory courses, will be doing a lot of optimization, where, for example, in the question, you have a firm, and the firm has a production function with some variable, which is K, usually capital, and L for labor. And what we're trying to do is that you want to find some optimization question where the firm wants to minimize its cost of production, subject to some sort of production target if it has, which in this question is noted as Q naught. So in a lot of these questions, we have to prove that there exists some kind of a combination of capital and labor inputs that really achieves this production target. So in this case, you'll later realize that when you're solving these kind of questions, you have to use the concept of compact sets and Weierstrass theorem, which is what we learn in basic calculus and analysis courses. So in this way, you can kind of see that when you learn calculus or analysis, the things you learn in those kind of classes, you use it implicitly when you're solving economic questions, and actually cannot get an answer unless you know that those analysis fundamentals really do hold in solving these questions. I just wrote down these answers. I didn't wrote it, I just found it on the net. It kind of shows that in the process, while you're solving these kind of economic questions, you're actually using what you learn from calculus analysis. But because we feel like it's so natural and so basic, sometimes we feel like we're not actually using calculus analysis. But in an implicit sense, we're using it every time when we're solving even some basic economic questions. So when you see the answers, you can kind of see how you're making some assumptions about the function, and students, we're trying to see if the cost function does attain some minimum value, which is actually the one we're looking for, because we're basically doing a cost minimization. So in order to do cost minimization, we have to find some minimum value. And in order to have that, you have to know about the properties of a compact set, and have to make some assumption that f, the function is a continuous function, which we already know is continuous by assumption. And using some properties of compact set and the continuity of a function, you kind of can show that there is indeed an answer to this question where you can get a cost minimization. There's a value for it. I'm not going to go deeply into how to answer this kind of question. There's just an example that shows that we're actually using a lot of concepts in analysis and calculus courses, and we're actually applying it into economics, but we're so used to it that we don't feel like we're using it. But in a way, you have to know this at some point, because if you want to know that you're going on the right path when solving some economic question or doing some answering some research questions, you have to know that the process you're using, like the tools you're using. So basically the mathematical logic that you're using are very sound, and they're not having a contradiction. Because if you know that later after you're solving some questions, that will become a very serious problem. So in order to know that what the logic they uses are very sound and it holds when you're solving the questions, we're going to learn about some basic analysis courses beforehand, before you go into the real economic questions that you have to solve. Okay, so this is just another. Sorry about that. So this is another some sort of question that you would use some sort of limit analysis related definitions or concepts in order to solve some questions. Like you have some question where a monopolist has a demand function and there's a cost function, and what you're trying to do is trying to show that as the value B approaches 0, the monopolist profit maximizing price will approach A over 2C. So this kind of questions, like as some parameter or some value approaches some values, you want to show that the monopolist price is also approaching some kind of value. And these kind of concepts we're using limit. So in order to solve these kind of questions, you have to know what limit means, and also has to use the concept of epsilon delta concept, which is very frequently used when you're trying to prove something in a limit term. And you encounter a lot of this epsilon delta concept when you're solving calculus or analysis courses. So you have to be very familiar with it in order to solve it without any problem. And I also wrote down some answers to this question, which is also, we're not going to go deep into it. I just found it on the net and just on the internet. So what I'm trying to kind of show that when you're trying to solve these kind of questions, you are using a lot of analysis courses, so analysis concepts. So even if you think you're not using it, actually when you're solving a lot of economic questions, you'll be encountering a lot of concepts that you learned in a calculus class or analysis class. So be aware of that and take it as like a motivation of why we are studying basic calculus and analysis even in our graduate level economics, because it's the basic of our logic. Okay, so there's a lot of things to know about when we're reviewing calculus, a lot of concepts and definition that we have to know. But before we start all that, we're going to have some kind of point where we're going to start our lecture. So that will be in our course, real numbers. Now you'll be kind of wondering why we are starting our review of calculus or analysis from the real number concept. Well, there are many reasons. Firstly, in economics analysis, eventually what we care about is, well, numbers. Even though we're dealing with very abstract functions or values that are abstract or values that are not defined, we're still trying to deal with numbers basically in the end. And in fact, that number is real numbers. It's not complex. Mostly it's not really about complex numbers or some integers. Mostly we're dealing with real numbers in general. So that's why we have to learn about real number first and why it's important. And also much of the mathematical objects or ideas we use in economics, which is like function, differentiation, integration, all of those concepts are based upon and is built upon real numbers. So if you don't know about the basic properties and qualities of real numbers, it's very likely that you'll get into some trouble after you're trying to do a more complex math analysis, such as mathematical objects and functions or differentiation. So in order to do these more complex computations and analysis, you have to know about the basis, which is the real numbers. Hence, it's very important to know about what real numbers can do and how they operate. Okay, I'll be giving you the attendance code. The attendance code is 32. 32. So this is for this session's attendance code. Let me just erase that. 32. Anyhow, let's move on. So our goal for the real number session is that we want to learn about how real number works, so how it operates. So we're trying to know about the basic properties of the real numbers. So in this session, we're trying to know how our basis is working and how real numbers, how they add up, how they operate, and what kind of properties they have. And these properties are very important because when you're learning about functions and other properties in mathematical analysis, we're using it as if it's given, as if it's very basic. So we have to know really about the basic fundamentals before we go on to a more complex definitions and concept in analysis. So just be tuned for it. Okay, so one of the very basic properties of real number is that it has no gap. So it's very simple, really. There is no gap in real numbers. You might think that why is so important, because actually a lot of the number systems you use, a lot of these number systems have gaps. For example, if you think about natural numbers, so it'd be like 1, 2, 3, 4, like this. So in a natural number sense, there are a gap. I mean, gap in the terms of real number, but still, just intuitively, if you see 1 and 2, you'll realize that there's some gaps between 1 and 2. Like there's, for example, there will be 1.5. But if you're just learning about, I mean, if you're just thinking in terms of natural numbers, 1.5 is not a natural number, so we're not thinking about it. So in a natural number term, these numbers are, 1.5 is a whole. So in a way, natural number does not have all the numbers between these numbers, like 1.5, 2.1, 2.2. So you can kind of see how there's a whole between numbers. So what if we go into a more deeper system where there's more numbers, such as integers, like integers, so they'll be like negative terms, right? So we have something like -1. So if you like in horizon, where if you go on to the left, you'll be going on to the negative number. If you're going on to the right, you're going into the positive number. So, but still, in an integer concept, there's still a whole. So for example, we still have the 1.5 problem, which is between 1 and 2, but we can't really have 1.5 as a number in an integer. And also in the minus sense, we also don't have minus 1.5. So which is also between that. So this is also very problematic. So there's still a whole, at least in a real number term actually, but just bear it with me. So in a way, but 1.5 is a very intuitive number in the sense we kind of get what it means, at least in real life. But in a system of integers, the 1.5 is excluded from it. So there's a whole, which makes it very uncomfortable, at least if you want to use it in our everyday analysis. So we want a more deeper, more denser number system. So one of it is the well-known rational numbers. So it's kind of hard to draw like the rational numbers from now, because it's a very it's a lot more denser number system than integers and natural numbers. So it's basically like a numbers where it's built as a division of two integers, for example, like, so it's this sort of like m over n concept where m and n are integers, like just word of notation. So the symbol you see right here, in case you don't know, this means that the left side is an element of the right set. So m and n are elements of z, and z is a usual notation for integers. So what this is really saying is that rational numbers are sets where it's a division of two integers. And just for your information, we have to make sure that n is not 0, because if n is 0, then it's not defined. So in this case, m and n are integers, and n is not 0. So these sort of numbers are what we call rational numbers. And there are a lot more numbers compared to real natural numbers and integers that we just described, which makes us feel that maybe rational numbers is enough to make sure there's no gap in the number system, which is kind of easy to think about, which is kind of like the very basic guess you can think about, because it's a very dense set. For example, like so we have 1 and 2 again, and rational numbers, unlike other number system, now contains a lot more numbers between 1 and 2. For example, 1.5 is also a rational number, so rational number also contains that, and it also contains a lot more numbers like 1.56, 1.57, 1.558, 1.555559. So it contains a lot more numbers now, the rational numbers. So you might think that now I think rational numbers is enough number system where you can kind of use freely without considering too much about the gap. But the problem is, even in the rational number system, there is also a gap. So I put it on the slide. So example, rational number also has a gap, and probably you kind of already know this. For example, if you took a lot of courses in undergraduate, you'll realize that there's such a number where the number is not a rational number. For example, like numbers like root 2. Root 2, yeah, right? I always forget like the notation, the name of the notation, but just let's say it's root 2. So root 2 is not a rational number. You can actually prove this. I'll give you like as you give it like an exercise, you can kind of show that root 2 is not a rational number. So in a way, what you would have to do is that you have to use some part where you kind of assume that it's a rational number and drive a contradiction out of it. So like you would assume that root 2 is you can kind of prove it using proof by contradiction. You can assume that the root 2 is some rational number, which would be division of some two integers, and you can drive a contradiction out of it. So you can kind of try this proof. And it actually becomes a lot more easier when you assume that n and m are, I'm not sure how to say this in English. Is the primary division, if those two are like prime numbers, like not prime numbers, but like in Korean word it's 서로수. So like they don't get divided by each other unless it's divided by itself or 1, something like that. So if you assume that root 2 is n over m, and then you can drive a contradiction out of it. So you can kind of try it. I'll leave it as an exercise. So root 2 is, okay, so in the end, what I'm trying to say is root 2 is not a rational number. But it is between 1 and 2. You might have seen it, but in a numerical computation, you can kind of see that root 2 is somewhere like, it's somewhere like 1.414 or something. So it should be between 1 and 2. But it's not a rational number. So this means that even a rational number has gaps. And you might be also more familiar with terms like pi, which is, let me just erase it. So you might be more familiar with numbers like pi. So it's like a number between 3 and 4, but it's not a rational number. So you can kind of see that even rational numbers has gaps. So that's problematic because we want to deal with as many numbers possible. So if you're dealing with numbers with gaps, if you're dealing with numbers with gaps, it's very problematic. We usually want to deal with numbers that has no gaps, at least as much as possible. So in that case, we resort to the real number system because the real number system includes all sort of these numbers. So as I said, the numbers like pi and root 2 is not a rational number, but it is a real number. So you can kind of understand why we're using real numbers, because real numbers are like the number system, like one of the most densest number system where there's just no gap in the number. So if you remember calculus courses or analysis, you remember like courses where you draw like a horizon. Like this for like number systems, and usually these horizons kind of mean like the real number because there's no gap. So it kind of shows like in a visual sense that there's no gap in the number system. So you don't really use this to describe like rational numbers or natural numbers. We kind of use this kind of to describe the horizontal line as like a real number system because it's like a no gap. And it's like, and the numbers are all continuously related and all there. So just for a quick introduction to the like visualization of real number system as a horizontal line. So the essence of this no gap property of real numbers is is known as a very famous property of R. And for another word for notation, if you in the slide, you can see kind of like the curly notation for R. So remember I said like Z is a curly Z notation is for integer sets. Normally when we describe real number system, we describe the curly R as the set of real numbers. So just remember that. So whenever I use R with the curly sign, just think of it as like a real number. So the sense of this no gap property of real number is very famous actually, and is given a name for it, and which is called least upper bound property, abbreviated to LUB, which we'll discuss about it in a minute. So what is this least upper bound property? So we're going to be thinking about some set where the set is written on slide A, which is set of all numbers that is smaller than root 2. And we again have another new notation, which is Q. And you might have guessed it, but we usually use curly Q for rational numbers. So we're thinking about a set A, where the set A has all sort of rational numbers such that these numbers, rational numbers, are smaller than root 2. So you have numbers like, let me just erase it. So you have numbers like 1, 1.3, 1.2, 1.1, etc. So all these sort of rational numbers that is smaller than root 2. So it would be like something smaller than 1.41, something like that. And we consider this set is non-empty, of course, by definition. You can kind of see already, like there's 1. So it's not going to be empty, the set. So it's a non-empty set. And we define element y in rational number as upper bound of the set A if this property is hold. That is, y is greater than or equal to all the x, which is for all the x in A. So what does this mean is that we're considering the set A, where the set A is a set of all rational numbers that is smaller than root 2. So we can consider also another element y in a rational number, where the rational number y is bigger than all the, which is bigger or equal to all the elements in set A. So consider a number like 2. So if you consider a number like 2, let me just write here. So number like 2, you can kind of see, like, remember the numbers that I just plotted here, like 1, 1.3, 1.2, 1.1. These are like all the elements in set A. And you can kind of see that all of these elements are smaller, at least equal, all small than the number 2. So what this kind of shows is that 2 are sort of rational number, such that all of the elements in A are smaller than this number. So we call these sort of numbers as upper bound. And you can easily see that there are going to be more than one of these upper bounds, because if you consider, because 2 is an upper bound for A, you can kind of intuitively see that 3, 4, 5, 6, 7, and all those numbers bigger than at least root 2. Like all the rational numbers bigger than root 2 is going to be the upper bound for a set A. So in this case, now we define what upper bound means. It basically means some sort of numbers that are bigger than all the elements in a certain set. So now we're going to consider a set of all these upper bounds. So we define set B as set of all rational numbers such that these rational numbers are upper bound of A. So remember that I told you there are a lot of upper bounds, like there will be 2, there will be 3, 4, 3.5, 2.5, those kind of numbers. So we're going to gather all of these numbers and put them in a set, which is set B. So set B is set of all these upper bounds, which is also non-empty, because we already showed that 2 is one of the upper bounds, so it's not going to be empty. Then now we have all these upper bounds, and now what we can think about is that whether the set B have smallest element. So remember that we're considering like the upper bound of A, where the A is all of the elements that are smaller than root 2. And root 2 is some numbers like 1.414. And the upper bounds and the elements in the rational number will be upper bound as soon as it's just a little bit bigger than 1.414 something something for root 2. So like 1.5 will be also upper bound, and 1.6 upper bound, and 1.49 is also going to be a rational number that is an upper bound for the number. But then you can make it very, very small. Can you see, like, I can get from 1.49 to I can go 1.498, which is also an upper bound, and 1.94987, which is also an upper bound, and 1.48, which is also going to be an upper bound. It's like there's numerous upper bounds, and very smaller one as we go smaller. But the problem is, in case of rational numbers, we can always find smaller upper bound. So as I wrote on the slide, 3 is an upper bound, 2.9, 2.8, 2.7, 2.4, 2.2, 2.19, 2.189. They are all upper bounds. And you can get smaller and smaller for every upper bound. And in a rational number, you can kind of see already intuitively, because root 2 is not a rational number, you can kind of see there is no smallest element. So you can get as small as you can, but you're not going to get the smallest element for the set B, at least if you're talking about rational numbers. This problem is solved if you change the Q to R. Because that's very easy, because if you think about, not in case of rational numbers, but in case of real numbers, just choose root 2 as the least element of B. You can kind of see that root 2 is going to be the smallest element that is an upper bound. So you can kind of see, because raising is like a pain. Okay, so you can kind of see that root 2 is going to be the smallest upper bound, because if you try to get a smaller upper bound for this set A, like for example root like this, you can kind of see that this is not going to be an upper bound for A, because you can always find some rational number that is between these two numbers, between root 2 and root 2 minus 0.0001. So they're going to be a rational number between them, which means that this is no longer an upper bound, because the fact that there is a rational number between these two numbers means this number, because it's smaller than root 2 at least, is also going to be a set A. But then in that case, there is some rational number that's bigger than this number, root 2 minus 0.00001. This shows that that can be an upper bound for set A. So we kind of see that root 2 is going to be the smallest upper bound. So this problem is solved. So the problem of having the smallest upper bound is solved if we change our number system from Q, the rational numbers, to R, real numbers. So unlike Q, R always has the smallest, or what we call the least upper bound. So root 2 in this case is the least upper bound. So here's our definition for the least upper bound. So upper bound are elements that are bigger than some sort of elements in some set A, in this case. And the least upper bound is the smallest of these upper bounds. So as I repeat again, unlike the rational numbers, real number system always has these sort of smallest, or now is least. So real number system always has these least upper bound. And we call this property as least upper bound property of R. Or sometimes we call this property as completeness of R. So we call system like real number as complete. You can kind of think of complete as having no holes. So basically, because there's always an element, smallest element of upper bound, the real number system does not have a hole. It's all complete. So in a sense, we also call this least upper bound property of R as completeness property of R. Okay, so we already thought about some properties of R in the sense of upper bound and being complete. There's also other property of our real number system that is very nice, which is that real number system is a field. So what is a field? Some of you might already know this, but to be very simple as possible, this just means it has very good properties. So like, this kind of means, it's like similar to saying that real number system, they add up well, and there's not much of a very weird process in arithmetic procedure. For example, you can see on the slide like 3.4 equals 4.3, 4 plus 3, which means like the addition has commutative property, which means if you switch the addition, it's not going to change the value. And the second one is you have a parenthesis on 3 plus 4, and the right hand side you have a parenthesis on 4.5, which kind of shows that this is, in a mathematical term, this is I think it's associated property, which means that as long as you have same operation, which is here summation, whether you do the left summation first or the right summation first doesn't change the value. And also the third one, if you just have -4 and just do negative for that, so you put minus up in the -4, you get 4. So these kind of very nice properties where we would want number system to have, R has this. And these properties are called field. Although it's not really specific to R, because rational numbers like Q also have these sort of field qualities. So it's not a specific property that R has, but still R also is a field, so it has a very nice property. So not only is R have no holes, but also has very good arithmetic properties. So as I put on the slide, in a sense, it just means real number system adds up very well without too much restriction or some very weird pathological properties like some numbers have. And also, another property of R is that R real number is an ordered set. So this kind of just means that you can always compare two numbers, which also very natural if you think about it, because if you have numbers such as 1 and 2, you immediately see that 1 is smaller than 2 and 2 is bigger than 1. So this kind of order is very natural, but depending on what number system you're using, you can have a situation where the number system has a very weird order system. So, and fortunately for the real number system, they don't have that, and it has a very natural order that we are very used to it. But this is also not very specific to the real number system, because systems like integers and rational numbers also have this order system. So I put on a slide, root 2 is bigger than root 3, and 2 is equal to 2. So basically what order means is that if a set is ordered, you can basically kind of show that you can kind of basically compare every point, every element. So you can always compare them, and it also has a very nice property such as transitivity, which is something like this. So if 1 is bigger than 2, and 2 is bigger than 3, right? And from this, we can easily get that 1 is bigger than, So 2 is bigger than 1, and 3 is bigger than 2. And from these two inequality, we can kind of guess that 3 is going to be bigger than 1, right? And these sort of properties are called transitivity property, and these properties are also defined on an order set. So order set means basically you can always compare two elements, and also the transitivity property holds. And R has that, which is also a very good property that we want to have. Now the question pops up, but still, we get the real number has a very nice property, but why R especially? Why are we using real number system as our like basic number system? Because we do have rational number and natural numbers, and you might know, but we also have complex number systems. So why are we really using R? I mean, R has nice stuff, like it has no holes, but I mean, that's it. So why are we using it? So there are a few reasons why. Well, one of the reasons which I didn't put up in the slide is that in mathematics and also in economics, we deal with a lot of situations about limits where some numbers tends to some numbers as some variables moves to that numbers. Like for example, n goes to infinity or n goes to some element. We deal with a lot of these limit situations, and when we're dealing with limits, usually we have to, it's a lot better if you just deal with these numbers in a real number system, because some situations sometimes, like rational numbers, because remember that there was a whole, so there are situations where some elements does not converge in rational numbers, while some numbers, while in the real number system, it converges very well. So when we're dealing with a lot of properties like limits, which I'll talk about in the next few sessions, it's very lot better if you deal with real numbers. And also, there's also a question you might have like, okay, I get real number is a good system, but I'm pretty sure there are also a lot of other other number system which also has some sort of no holes property and also has a very nice ordered field property. So why are we just focusing on real number system though? Why? Just other than the fact that it's very realistic numbers. And now I want to like refer to some very math stuff. So you don't need to remember, just kind of think of it as like a reference. So in a math theorem, what we can actually prove is that a complete ordered field, like which is the real number. One of the example of the complete ordered field was real number, right? Remember, like completeness is least upper bound property, and R was ordered and it was a field. So numbers, so number system that is complete and ordered field, like real number, is unique up to isomorphism. So you might be kind of amused about this term of isomorphism and stuff. I'm not going to explain about what isomorphism is, so I'm just going to tell you intuitively what it means. So basically what this means is that even if you use some other number system that is also complete, ordered, and a field, that is just similar to the real number in a sense. So in a sense, even if you deal with some other number system that is also complete, ordered, and a field, that is actually, in a sense, it's just similar to real number system, except that some notations or terms are different. So because of that reason, because R is very familiar and it has very nice property and it's unique, at least in a sense of completeness and orderedness and property of a field, it's very natural that we just use the real number system as our basic number. So that's all you have to remember. And before we end the session, I want to talk about some very useful properties of R and Q and maybe some natural number as well. New notation, curly n means natural number. Okay, so first property is that Q is dense in R. So what does this mean? So actually this is very intuitive. So what this means is that I wrote it on the slide. So for any interval x and y in R, where x is smaller than y and xy is of course real number, there is some rational number R such that R is between these two numbers. So what we can see is that the term Q is dense in R means there's always going to be a rational number between two different real numbers. For example, like intuitively, think about 1 and 2. So 1 and 2 are also real numbers and they're different, right? And 2 is bigger than 1. So any 1 and 2, there's going to be a rational number between them, like 1.5, right? So that's the meaning of Q is dense in R. And also, think about 1.5 and 2. Like, note that 1.5 and 2 is also real numbers, and then they're different, right? So we can also find a rational number between these two numbers, such as 1.7, right? And because 1.7 and 2 are also different real numbers, you can always find a number between them like 1.9 and so forth. So what this means is that as long as two elements in a real number system is different, you will always find some rational number between them. And it's a very nice property that you can use later on. So just remember that. And second very nice property is called Archimedean property, which is, I wrote it on the slide again, which is for any positive number x and y, there is some positive integer n, such that nx is y. So it kind of feels a bit complicated, although it's very intuitive. So basically means that you can always find some very large natural number that's going to be bigger than some integer. I mean, think about it. Like, it becomes more easy if you think about x to be 1. So then the equations, like inequality in the slide, will be like where y is just a number, y is just a positive number, and n is a natural number, right? So for any y, you're going to find some number bigger than y. Like, for example, like this, like if you, and for any number y, just add one number plus 1 to it, and it's going to be bigger than y. So it also is a very intuitive property, but we made it into a theorem, like a property or theorem, so you can use it and use it to solve some questions. I'm going to be talking about how we use this to actually solve some problems in limits and some other properties and analysis. We'll talk about that in the next session, I think. So just remember these two very useful properties. We'll be using them throughout our analysis course. And I just want to very briefly talk about extension to the multi-dimension R. So sometimes it's very useful to think about multi-dimension space. So for now, we only talk about real number where the R is just a number. But we can also think about a space where there's like an n tuples of numbers, right? Like something like this, kind of like a coordinate. So it's like a 1, 2, 3. So like this would be like a space where it's 3-dimension space, and the x-axis will be x-axis number is 1, y-axis is 2, z-axis is 3, like that. So like 3-dimensional spaces, we also have 2-dimensional spaces and n-dimensional spaces. So it's sometimes very useful to think about number system in a multi-dimension. For example, in economics, you can think about a product space where there are more than one products. For example, I put some example here. So we can consider Rn space, where it is basically a space of n tuples like x1, x2 to xn. So in math, we usually call this sort of spaces as Euclidean spaces, and they're very useful, especially in economics, because, for example, in a lot of the real world, when we're dealing with economic theory and data, there are going to be not just one product, but there are going to be several products, and we can treat these different products as if they're occupying each spaces. So we can think about multi-dimensional product spaces where consumers basically think of each dimension as a different product. So we're thinking of x size as different products. For consumers who will buy, for example, x1 is gum, x2 is water. So we can think about this n tuples of space, multi-dimensional Rn space, as some sort of product spaces that consumers can buy out of. Like x1 is gum, x2 is water, x3 is car. So each dimension refers to different products that the consumers can buy or not. So we can think about this very multi-product space using the concept of multi-dimension. So I just wanted to talk about this before we end our brief talk about R. So this is the end of the session for real numbers.